Hello everyone, my name is Koma Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to our video, continuing our lesson on momentum and the law of conservation of momentum. In this video, we will be doing an example to illustrate the concepts that we covered on a separate video. Okay, so the question that I will be solving in this video is from a past question paper, from a past exam question paper, which is from the year 2012. Okay, so we are going to solve that question, and we're going to illustrate the principle of momentum and the law of conservation of momentum. Okay, so let's jump right into it and let's have a look at the question. Okay, so the question is as follows. Okay, so as mentioned, it's from a past paper, from a 2012 past paper, past question paper from an exam, November. Okay, so it says the diagram below shows a car of mass m. Okay, it shows a car of mass m traveling at a velocity of 20 meters per second east on a straight level road, and a truck of mass 2m traveling at 20 meters per second west on the same road. Ignore the effects of friction. What does this mean? What does ignore the effects of friction mean? Okay, so I like to do this. I like to break down the question before we actually get to answering the question. Okay, so what we have here is the following situation. We've got a car moving at a velocity of 20 meters per second to the east. Okay, and then the east is that direction. Remember, momentum is a vector, so it's always important to specify the direction. Okay, and then we've got another vehicle moving from the west, right? Moving from the west, from the east towards the west, right? It's moving towards the west at that same speed. Velocity is equal to 20 meters per second. Okay, and then that's another vehicle. That's that vehicle there. That's that truck there. Okay, and the mass of the car is m. Okay, and the mass of this vehicle is 2m. And they told us to ignore the effects of friction. What does what does this mean? What does this tell us? So this tells us that there is no external force. There is no net external force acting on this car or on this truck. Okay, there is no net external force acting on this car or on that truck. That's what they mean when they tell us that we should ignore the effects of friction, right? If we ignore the effects of friction and there is no other applied force being shown acting on the objects or on the cars, in this case on the vehicles, then there is no net external force. So the net external force is equal to 0 on both the cars. Okay, that's a bit of important information that they are giving to us when they're telling us to ignore the effects of friction. Okay, let's continue reading through the question. Okay, so the question then down there further says, the vehicles collide head-on and stick together during the collision. Okay, the vehicles collide head-on and stick together during the collision. Okay, so what happens is that as these vehicles are approaching one another, they collide. They meet at a point. Say they meet at that point and then they collide, right? They collide. Say the car collides with the truck there. There's the truck there, and then they collide like that, right? And then after colliding, they continue moving together either in this direction or in that direction. We don't know yet. Okay, but what we know is that once they collide, they stick together and then they move together in a single direction. Okay, so that's what is happening here. So you've got this truck and you've got this car, and they are moving at the same velocity of 20 meters per second towards one another, right, in opposite directions, and they collide. Once they collide, they move together in either the east or the west direction, in one of the two directions that one of the vehicles was coming from. Okay, so let us see what they are asking us in this question. Now that we've established what's happening in the question, let's see what is required of us. Okay, so 4.2 here says state the principle of conservation of linear momentum in words. Okay, and this is worth 2 marks. State the principle of conservation of linear momentum in words. Well, that is quite simple from the previous video, right? There are keywords. Just know that, note that for these types of questions, the marker, the examiner marks, they look for the keywords. If you don't include these keywords in your answers, then you won't get your full marks for the answers, or you won't get your marks for the answers. Okay, so the principle of linear momentum in words. Principle of linear momentum. Principle of linear momentum. And as I'm writing this down, I will point out the keywords that you should not forget whenever you're stating this principle. Okay, so the principle of linear momentum states that the total momentum, there are several ways that you can say this thing, but I'll point out the important words, right? The important words. So the total momentum in a closed, let me write that a bit better, in a closed or isolated system. You don't need to say or isolated. If you say closed, you don't need to say isolated. If you say isolated, you don't need to say closed. Okay, so let me just say closed dash isolated. Closed dash isolated. The total momentum in a closed or isolated system remains constant or does not change, or is constant. Okay, so the keywords in this answer are as follows. The keywords are closed, right? If you say closed, you don't have to say isolated. If you say isolated, you don't have to say closed. So the total momentum in a closed or isolated system remains constant. Okay, so you've got to say it remains constant, you've got to say the total momentum, and you've got to say closed or isolated system. Okay, and then this is so what is most likely going to be marked. Remember, this question was worth 2 marks. So the closed system is probably going to be worth a mark, and the constant is going to probably be worth a mark, right? Or the total momentum is probably going to be worth a mark. I'm not really sure how they would mark that, but these are all the important keywords. Just make sure that you include all the important keywords. Make sure that you state the principle properly, and you take into account every little aspect that you should take into account in your description. Okay, so that's basically straightforward. That's 4.2. That's you should get your 2 marks from this, right? Another way you could say this is that the impulse in a closed system is constant, right? The impulse is 0, rather. The impulse is 0. Okay, so in other words, there is no change in momentum, but we'll cover that in a separate video when we look at impulse. Okay, so yeah, the impulse is 0. So okay, let's look at the second question of this. That was easy enough. That was worth 2 marks, so that was fine, straightforward. Now 4.3 says calculate the velocity. Oh, by the way, I erased 4.1 here because 4.1, you can see that this starts from 4.2. I intentionally removed 4.1 because it was a different concept and I don't want to mix concepts up. Okay, so in this video, I just want to focus on momentum, strictly momentum. Okay, so 4.3 says that calculate the velocity of the truck car system immediately after the collision. Calculate the velocity of the truck car system. Notice that they're saying the truck car system. What do they mean by the truck car system? This is what they mean. Remember, initially you had the following. Initially you had a car. You had a car with a velocity of 20 meters per second. And you had a truck, right? You had a truck. I know my truck looks bad. Let me do that. Okay, you had a truck. That's a canopy there at the back, whatever. You had a truck with the velocity of 20 meters per a second, moving in that direction. This is what is happening initially, right? What is happening finally? Well, what is happening finally is that the truck and the car collided, right? They collided. The truck and the car collided. They collided, right? Now, once they collided, they moved as a unit in the same direction with the same speed. They either moved that way or that way. That is what they're asking us to find out, right? They moved, as you can see, that they collided and they combined right now. They are a single unit. They are a single unit. And because they're a single unit, they continue moving. They don't stop moving. They continue moving, right? They will either move in one direction or the other. The question that we're being asked right now is we are asked to calculate the final velocity of the truck car system, meaning the truck and the car while they are moving as a unit. We are asked to calculate their velocity because it's going to be one velocity because they're combined, they are united, they are moving with one velocity. That velocity is what I'll call Vf, and we are asked to calculate what that velocity is. But I want you to remember that velocity is a vector. Since velocity is a vector, it has a magnitude and a direction. So not only do we have to calculate the magnitude of the velocity, but we've also got to calculate the direction of the unit, the truck car system. We've got to calculate if it's traveling towards the east or towards the west. Okay, so let us do that. Okay, so let's solve 4.3. So that's 4.3. Now, before you solve these questions, it is good practice, and it is actually what I am recommending to you. You do this, you will get marks for this. You might get marks sometimes you might not, but it is best practice to do this. Establish your sign convention. So decide if east is positive or negative. Decide if west is positive or negative, right? It won't always be east or west. It could be left or right. It could be up or down. You know, it could be any of those four directions: up, down, left, or right, or whatever, right? Or even if you're at an incline, you know, up, the sloped incline could be up, and then the positive sloped incline could be up and the negative sloped incline could be down, whatever. Just decide on a sign convention. In this case, we've got, we go back to the question here, notice that the question there by the truck, right next to the truck, we've got arrows, right? We've got a north arrow and an east arrow, and the east arrow is pointing towards the right and the north arrow is pointing upwards. So let's see if I can show that to you. Okay, so I'm talking about that there. The north arrow is pointing upwards and the east arrow is pointing to the right, right? Now you've got to establish your sign convention. Let's establish the sign convention. I'm going to say, sign convention is basically you just saying which direction is positive and which direction is negative. That's all, right? There's no fancy way that you have to say it. You just have to let the examiner know which direction you consider to be positive. So you could do it a number of ways. You could say, just make sure that they know that you are specifying your sign convention, right? So I'm going to say sign convention. Then I'm going to say an arrow there. There's my east is positive, right? Like that. And then north there, N positive, right? Or you could write out an actual sentence. You could say east is positive. You could say east is positive, and you could say north is positive. North is positive, right? You could say north is positive like that. Now, there's no reason why you should choose east to be positive and north to be positive. They could be negative. Both of them could be negative. East could be negative and north could be negative. You have to decide, right? You can decide. No one can decide for you. You can decide. So what I'm choosing right now is simply a preference. I want anything that moves towards the right, towards the east, to be positive, and I want anything that moves up to be positive. So if I want my east to be positive, then it means then my west is going to be negative. Also, you don't have to specify it in terms of east and north. You can specify it in terms of west and south, right? You can say west is negative. You can say west is negative, and you can say south is negative, right? So basically the point that I want to drive across is that your sign convention is up to you. You decide on the sign convention. What's important after you decide on the sign convention is that you stick to it. Stick to your sign convention, right? Don't say one thing and then do another in your calculation, right? So let's actually do the solving of this thing here. Okay, so just to recap, we know that we've got a car. I'm just gonna write down the data that I have for the car. The car has a velocity of 20 meters per second, and it has a mass of m kilograms. Okay, and the truck has a velocity of 20 meters per second and a mass of, if I remember correctly, 2m kilograms. Okay, let's just confirm that the truck has a mass of 2m. Yes. Okay, so remember that this truck is traveling that way and the car is traveling that way. It's important to specify directions. So in other words, this car is traveling to the east and this truck is traveling to the west. Okay, right. The car is traveling to the east and the truck is traveling to the west. Now we know that the law of conservation of momentum states that in a closed system, the total momentum is conserved. Remember from our lesson on momentum and the law of conservation of momentum, if we have two bodies moving like this in a system, in a closed system, in a system wherein there is no external net force, then this car has its own momentum. I'm going to call it P1. In fact, I'm going to call it PC for momentum of the car. And then I'm going to call this PT for momentum of the truck. Doesn't matter what you call these things. You can call these things whatever, as long as you specify what these things are, right? So momentum is in P, so I'm going to say P sub C. PC is the momentum of the car, and PT is the momentum of the truck. This car and this truck exist in a closed system. How do we know that they exist in a closed system? Because we were told to ignore the effects of friction, right? And there is no other net external force that is shown that is acting on this car or on this truck, and there is no friction, right? There is no friction between the wheels and the road. Since there is no friction between the wheels and the road, and there is no other force that is shown that is acting on these vehicles, then it means that this entire system is a closed system. Since this entire system is a closed system, then the total linear momentum is conserved. By linear momentum, it just means momentum in a straight line, right? In the direction of travel. The direction of travel is in a straight line here. So the total linear momentum, and just by the way, just to be safe, you can say the total linear momentum here in the first instance, where we are asked to state the law of conservation of momentum. You can say the total linear momentum. Okay, just to be safe, right? It's a good word to include there. Okay, so that's just a side note on that. Okay, so here, back to this thing here, we've been asked, remember what we've been asked to calculate the final velocity of the car truck system once they collided and they're moving as a unit. Now, the law of conservation of momentum states that the total momentum in this closed system is conserved. What is the total momentum in the system? Well, it is the momentum of all the bodies that are involved in the system. What are the bodies that are involved in the system? It's the car and it's the truck, right? So you've got to add the total momentums of the car and the truck. But what does adding the total momentum of the car and the truck have to do with anything? Because we've been asked to find the final velocity. So why are we dealing with momentums if we are trying to calculate the final velocity? Well, because we are trying to use an equation that has the final velocity in it. In order for us to calculate the final velocity, we've got to use an equation that has a final velocity, right? We can't solve for the final velocity if we don't have an equation that has it, right? So that's and we know that the equation that shows the total momentum to be conserved has that final velocity in it. We'll see what I mean just now. Okay, so we know that this is a closed system. We know that the total momentum of this closed system is the total momentum of each of these bodies. So you just take the momentum of each of these bodies and you add it together, and that momentum that you get is the same momentum that you must end up with, because the total momentum remains constant. It does not change in a closed system. Okay, so what you're going to do is say total momentum before is equal to total momentum after. Before what? Before collision. Total momentum before collision is equal to total momentum after collision. Okay, what is the total momentum before collision? Well, total momentum before collision is the momentum of the car plus the momentum of the truck. Okay, which is equal to, what is the total momentum after the collision? It's the momentum of the car plus the momentum of the truck. Still, right? This is, I'm going to say initial, and initial. Then I'm going to say final, F for final, F for final. So the total momentum of the car initially plus the total momentum of the truck initially is equal to the total momentum of the car after finally plus the total momentum of the truck finally. Right, that's what those mean there. Remember, this is up to you. How you represent these things is up to you. Just state what they mean. It's totally up to you. Just state what they mean. They can't penalize you for putting in a different symbol than this, right? Okay, so that's what that means. So what is the momentum of all of these terms that we've included in the equation? What are the total momentums? Okay, so remember what the equation for momentum is. The equation, generally speaking, the equation for momentum is P is equal to M times V. This is the equation for momentum. Now, for each one of these things, for each one of these terms, you're going to have that P is equal to MV, but for each one of the objects. Okay, so let's do that. By the objects, I mean the bodies, which is the car and the truck. So let us do that. Firstly, let us start off with this one. The momentum of the car initially, before the collision. What is the momentum of the car before the collision? So you've got M times V. Okay, firstly, let me just say the momentum M, mass of the car, right, times the mass of the car times the velocity of the car, I'm going to say initially. Just express these better. Mass of the car initially, right, times the velocity of the car initially, right? That's PCI. That's done. That's the momentum of the car initially. That's M and V. Remember, momentum is equal to M and V. There's my M and V there. So the rest of the letters are just specifying what object I'm talking about. So that shouldn't confuse you. Okay, so the fact that I'm saying MCI and VCI, C just means car, I means initially, right? The important thing is that I have my M there, my mass. Okay, so my mass of my car initially times the velocity of my car initially, that's the total momentum of the car before the collision, right? Plus the momentum of the truck initially times the velocity of the truck initially. That's the momentum of the truck, right? The momentum of the truck is M times V, right? The mass of the truck times the velocity of the truck initially is all equal to this here, PCF and PTF. Now the momentum of the car finally plus the momentum of the truck finally. Now remember in this situation finally that this is what happens after the collision. And after the collision, we have that situation where the car and the truck are stuck together. Okay, we have this situation where the car and the truck are stuck together. Now, since they are stuck together, you will agree with me that the total mass of the car and the truck will be the sum of the individual masses of the car and the truck. So it will be the mass of the car plus the mass of the truck. So it's going to be the mass of the car plus the mass of the truck once the collision has taken place, because they are moving as one. They're acting as one. They are united. So their masses are combined, just like their velocity is combined. Okay, just like their velocity is combined, their masses are combined. So if we go back down here, then you will agree with me that the total momentum can be expressed as the mass of the truck plus the car, right? The mass of the truck plus the mass of the car. Or differently, put differently, I can say it's gonna be the mass of the car finally plus the mass of the truck finally. Okay, it's the mass of the car plus the mass of the truck after they've collided, right? All of this is a single m, right? This is 1m, this is one mass. Why is it one mass? Because they are moving as a unit. They are combined, therefore they have one mass, and the mass is the total mass. That's the total mass, m total. It's the total mass of the car and the truck. Okay, now remember, momentum is mass times velocity. So we should multiply this total mass times the total velocity. I'm going to say Vf total. Final velocity, Vf total. Okay, so that's what this equation looks like. This equation looks like that. I'm just going to erase the m total there. Okay, and then so this is what the equation looks like. So this is the equation, right? Now, if you take a look at this equation, what are we looking for? We are looking for that value there. Remember, from the question that we were asked to solve, we were asked to 4.3 down there says calculate the velocity of the truck car system immediately after the collision. The truck, so we want the final velocity. We want that velocity there, that final velocity of the truck car system. Okay, so in order to solve for that final velocity, we should have all these other parameters in this equation. Okay, so let's just substitute and see what we get. Hopefully it works out to something nice. So we're going to start off with MCI, the mass of the car before the collision. What is the mass of the car before the collision? Let's go back to our diagram that we drew up here and see. The mass of the car before the collision, we didn't get an actual number, it's just m, right? It's m kilograms. So that's what we're going to substitute, because that's what we've been given. We're just going to substitute m. So we're going to substitute m, then we're going to say times, what is VCI? Velocity of the car initially, right? That's the velocity of the car initially. So if we go back up there, the velocity of the car initially is 20 meters per second to the east, right? Remember, I said sign convention before you start solving these questions. Specify your sign convention. We said east is positive, right? We said east is positive. So then we're going to put in a positive 20. So this is going to be m times 20. Okay, so VCI is 20. So that's going to be m times 20. And it's a positive 20 because east is positive, right? Then we're going to come to MT, the mass of the truck initially. What is the mass of the truck initially? The mass of the truck initially is 2m, right? 2m kilograms. So we're going to say plus, this is that plus there, 2m. That's the mass of the truck initially, right? What is the velocity of the truck initially before the collision? The velocity of the truck before the collision is 20 meters per second. But we can't just write 20 meters per second. We have to specify the direction. If we said east is positive, then west has to be negative. So then that is minus 20. Okay, so that is minus 20. So we're gonna come down here and we're going to say 2 times minus 20. Okay, so that is what VTI is. Okay, then we're going to say equal to, which is that equal sign there. We're basically just substituting, right? Okay, then we come down here to this this mass here. Okay, so that mass there, we simply just add up the total masses. So we know that MCF, this is the mass of the car after the collision. Now the mass doesn't change. The mass of just the car individually doesn't change. So we know that the mass of the car is M, so that's going to be M here, right? Then that's MCF. The mass of the truck on its own doesn't change, so that's still going to be 2M because the truck weighs 2M, right? But then the total mass there, you're going to add it. You see it's M plus 2M, you're going to add it eventually. So then that's that V total that we are looking for there. So that's VF total. VF total. Then once I have substituted my things, then I can solve, see what's going to happen here. Now I just simplify this equation. Okay, I'm going to go back to black pen. I'm just going to simplify. What is M times 20? That's 20M, right? That's 20M. Then what is minus 20 times 2M? That is minus 40M is equal to, what is M plus 2M? M plus 2M is 3M, is equal to 3M times VF total. Okay, times VF. I'm just going to call it VF there. Okay, now we can solve. What is 20M minus 40M? This is minus 20M is equal to 3M VF. Okay, now if I divide both sides by 3M, if I divide both sides by 3M, what I'm going to get is the 3M there's, the 3M's there are going to cancel. Then I'm going to have, I'm going to go back to black. VF is equal to minus 20M. The M's there are going to cancel. So it's going to be minus 20 divided by 3 is equal to VF. Okay, minus 20 divided by 3 is equal to VF. Therefore, that's the velocity. VF, the final velocity that the truck car system will be moving is equal to minus 20 divided by 3. What is minus 20 divided by 3? Let's go to our calculator and see how much that is. What is minus 20 divided by 3? That's going to give us 6.67. Let's say minus 6.67. So VF is equal to minus 6.67 meters per second. Okay, or you can say you can write your meters per second like this if you prefer. Meters per second, meters per second. You can write it out like that. It doesn't really matter. Okay, so now what does this mean? Let's interpret this answer. You can see that this answer has a negative sign on it. Since it has a negative sign, remember what our sign convention was. Our sign convention was as follows. We said east is to the east is positive, right? So then it follows that west is negative. Okay, so if my answer has a negative sign on it, it means that the car truck system is moving towards the negative side. And which side is the negative side? The side that is the negative side is the west side. So the west side. So the truck car system is actually moving towards the left at this speed. So another way you can express your answer, if you can say VF, the final velocity is equal to 6.67 meters per second to the west. Specify your direction, to the west. Now, it doesn't matter which sign convention you had chosen, you were going to get the same answer in the end. In the end, you were going to get this answer, 6.67 meters per second to the west. Okay, so if we have to go up to the sketch to illustrate what is happening is that this car and this truck are initially moving towards one another at that velocity. Then they collide. Once they collide, they continue to move. But in which direction do they continue to move? They move to the west. In other words, they move towards that direction at that velocity that we calculated to be 6.67 meters per second. Okay, so that's the very basics of momentum and the law of conservation of momentum in a closed system, right? That's momentum in a closed system. It is conserved, it doesn't change, and you just take the momentum, the total momentum that you had before, you equate it to the total momentum that you have after, and then you just solve for whatever parameter that they asked you to solve for, and then that's it. Okay, it's not gonna get any more simpler than that. That's as simple as it can get. Okay. Okay, so that's it. That's the example calculation for momentum and the law of conservation of momentum. We will carry on with this topic in the next couple of videos. Till next time. Lesson number one.